Keeper 3.1, the limit of a sequence. Alright, so a sequence can be written as like a list of numbers in the form of like a sub 1, a sub 2, a sub 3, and all the way out to a sub n. You can also write a sequence using a curly bracket with a sub n in it, or you can write the curly bracket with a sub n in it with n equaling 0 as a subscript and infinity as your superscript. In other words, I'm telling you to go from 1 to infinity. Alright, so the limit definition of a sequence, basically, you're just taking your sequence and you're finding the limit of it, or you're trying to find what your sequence approaches as n approaches infinity. If the limit exists, we say that it converges or is convergent. If it doesn't exist, or if we get infinity, we say that the sequence diverges or is divergent. So for our first example, we have the limit as n approaches infinity of n plus ln of n over n squared. And so I'm going to start by taking the limit of the top, which I get infinity. Take the limit of the bottom, which I get infinity, which tells me I can use L'Hopital's rule. And so I can take the derivative of the top over the derivative of the bottom to get the limit as n approaches infinity of 1 plus 1 over n over 2n. Cleaning that up, multiplying everything by n, or just plugging in the limit straight up. I guess it would be easier just to plug it straight up in this case. I'd get 1 plus 1 over infinity, which is, remember 1 over infinity is 0. So on top we're left with 1 over infinity, which is just 0, which means that this limit does converge to 0. In example 2, it says determine whether a sub n equals negative 1 to the n is convergent or divergent. Since negative 1 to the n is actually an alternating function, like if n is even, I get 1, and if n is odd, I get negative 1. I'm going to take the limit separately. So I'm going to do n is even, the limit as n approaches infinity of negative 1 to the n is 1. N is odd, the limit as n approaches infinity of negative 1 to the n is negative 1. Since 1 does not equal negative 1, the limit does not exist. Therefore, the sequence is divergent. Alright, so we have a theorem that says that if you can find the absolute value of a sequence, and that absolute value equals 0, then the limit of the sequence itself also equals 0. So again, if you take the absolute value of something that maybe is alternating or is negative, and you take that limit and you get 0 out, then that means the limit of the original sequence is also going to converge to 0. Alright, so for example, we have determined if negative 1 to the n over n converges. And so instead of dealing with negative 1 over n to the n, I'm going to take the absolute value of that, and I'm going to find the limit of the absolute value of negative 1 to the n over n. Well, the absolute value of negative 1 to the n is simply 1, so now I have the limit as n approaches infinity of 1 over n. If I plug in infinity, I get 1 over infinity, which is 0. Since that equals 0, since the absolute value equals 0, that means the actual function itself also converges to 0, and therefore the original sequence converges. All right, we have something called the squeeze theorem for sequences, which we've dealt with squeeze theorem before in Calc AB. Very similar concept. If you have two functions and then a function in between those two functions, if the limit of the outside functions approaches some number L, then that means the inside function also approaches that number L. So think about it logically. If they're squeezed, if a function is squeezed in between two other functions or sandwiched in between two other functions, if those two other functions are approaching a single number, then that inside function must also be approaching that number as well. All right, so we have another theorem that says if we're given a sequence of the form x to the n, so something like a geometric type sequence, the sequence is going to converge from any number between negative 1 and 1 is going to converge. Now, if you have anything greater than 1 or less than negative 1, then it's going to diverge. All right, so here's an example. We have determined the sequence converges or diverges. A sub n equals 3 to the n over 4 to the n plus 1. All right, so I'm going to take the limit of that sequence, but before I take the limit, I'm going to rewrite the bottom to be 4 times 4 to the n using exponent rules. And then I'm going to rewrite it one more time to kind of make it more geometric or exponential-ish. So I'm going to rewrite it as 1/4 times 3/4 all to the n. Now I'm going to plug in my limit of infinity. So I get 1/4 times 3/4 to the infinity. Now, again, I can use that theorem that we just saw in the last slide. Since 3/4 is less than 1, I know this thing is going to converge. But you can also think about it just in general, like graphically, 3/4 to infinity is approaching 0. And so I have 1/4 times 0, which is 0. Therefore, the sequence converges. Now in this example, I'm going to do the same exact thing, except for I'm not going to do as many steps because I'm just going to look at the x value. So first thing I'm going to do is rewrite this as 5 to the n over 3 to the 2n. Then I'm going to rewrite that denominator instead of 3 to the 2, and I'm going to write that as 9 to the n. And so then I can rewrite it as my exponential and have it as 5/9 to the n. Since that 5/9 is less than 1, I know my sequence converges. All right, so we have some new terminology. The first one is that a sequence is increasing if the current term that you're on is less than the next term. So if you're on, say, the 5th term, and the 5th term is 9, and then the 10th term is 10, I know that my sequence is increasing. Now, vice versa, I could do that for decreasing. If the current term that I'm on is greater than the next term, I know my sequence is decreasing. If a sequence is either all increasing or all decreasing, we call that sequence monotonic. All right, so this example asks, is it increasing, is it decreasing, or is it not monotonic? In other words, is it like going backwards and forth, not increasing or decreasing? So we actually have two methods to show this, and it's really important because we do this quite often in this unit. The first method is to show that either the term that you're on is greater than or less than the next term. So what I'm going to do is I'm going to start with the current term. I'm going to call that n. And then the next term, I'm going to call it n plus 1. And I know that n is less than n plus 1. Now what I'm going to do is I'm going to build my function. Remember, the function we're dealing with, or the sequence we're dealing with, is 3 over n plus 5. And so I'm going to build that function on the left-hand side of my inequality. So what I'm going to do is first I'm going to add 5 to both sides. So I have n plus 5 is less than n plus 1 plus 5. Then I'm going to make it a fraction. Now remember, when you make it a fraction, you have to change your inequality sign to be greater than. So I have 1 over n plus 5 is greater than 1 over n plus 1 plus 5. So again, change your inequality to switch whatever sign you're on. And then the last thing to build my equation, I'm going to multiply by 3. So I get 3 over n plus 5 is greater than 3 over n plus 1 plus 5. So here I see that the current term that I'm on, which is 3 over n plus 5, is greater than the next term of 3 over n plus 1 plus 5. Since it's greater than, then that means that my sequence is decreasing. All right, so the term I'm on is greater than the next term, means I'm decreasing for all n. So that was method 1. Method 2, we could also just take the derivative of the sequence to see if it's negative. And if we can show that the derivative is negative, then we know it's decreasing for the entire function. So what I'm going to do is I'm going to take my function, take the derivative of it. I have to go ahead and do quotient rule. So I'm going to do low d high minus high d low over low low. Simplifying that out, I get negative 3 over n plus 5 squared. Thinking about this just in terms of numbers, not specific numbers, but I'm getting a negative 3, which is a negative number on top. And then on the bottom, no matter what that n is, I'm squaring it, so I'm getting a positive number. A negative over a positive is a negative number. Therefore, since the derivative is negative, I know my sequence is decreasing. Now, both methods are equally as important. You need to know both methods in this unit. And you'll see I'll use them interchangeably. Some equations I use method 1, some equations I use method 2, depending on which one in my mind I see as easier for that function. All right, we have some more new terminology. We say that a function is, or a sequence is bounded above by m if you have like a number that you're approaching that it can't go past that number at all. And then it's bounded below by m if you can't go below a certain number. So again, like you have a max number and a min number, we're bounded. And so if you're bounded above and bounded below, we call it a bounded sequence. All right, so example 7 says, is a sub n equals n over n plus 1 a bounded sequence? So what I'm just going to do is look at a couple of numbers. Start with n equals 1, which would be our smallest n. So I get 1/2, then n equals 2 is 2/3, n equals 3 is 3/4, and so on, all the way to n equals infinity, which would be the limit as n approaches infinity of n over n plus 1, which is 1. So it looks like the smallest number I have is 1/2, and the largest number I have is 1, which means that my sequence is bounded from 1/2 to 1. All right, so our last thing is a theorem that says, hey, if your sequence is both bounded and monotonic, then it is convergent. But you can't have one alone. It has to be both, either bounded or both bounded and monotonic. You can be bounded but not monotonic and be divergent, or monotonic and not bounded and be divergent. But if you are both bounded and monotonic, then you are convergent.